Section 1 Introduction. In this introduction, we discuss the challenge of aligning large language models, LLMs, to follow instructions accurately. This usually involves fine-tuning the models using a significant amount of human annotated instructions or preferences, or using outputs from more powerful models. Recent studies have emphasized the importance of the quality of human annotated data. However, it's difficult to scale up the process of annotating instruction following datasets with high-quality data. In our research, we propose a different approach. Instead of relying on human annotated data, we use a large volume of unlabeled data to create a high-quality instruction tuning dataset. We achieve this by developing an iterative self-training algorithm. This method allows the model to generate and curate high-quality training examples to enhance its own performance. Our approach, which we call Instruction BackTranslation, is inspired by the traditional back-translation method used in machine translation. In this method, sentences written by humans are automatically annotated with model-generated sentences in a different language. Our method begins with a basic instruction following model and a web corpus. The model is first used to augment its own training set. For each web document, it generates an instruction following training example by predicting a prompt or instruction that would be correctly answered by a part of that document. However, training directly on such data has shown poor results in our experiments. This is due to the varying quality of human-written web text and the noise in the generated instructions. To address this, we demonstrate that the same basic model can be used to curate the newly created augmentation data by predicting their quality. The model is then self-trained only on the highest quality pairs of instructions and outputs. This procedure is repeated, using the improved model to better curate the instruction data and retraining to produce a better model. Our final model, which we've named Humpback, outperforms all other existing non-distilled models on the Alpaca leaderboard. In summary, Instruction BackTranslation is a scalable method that enables language models to enhance their own ability to follow instructions. Section Summary. In this section, the authors discuss a method called Instruction BackTranslation that leverages unlabeled data to create a high-quality instruction tuning dataset. They use a self-training algorithm where the model augments and curates training examples to improve its own performance. By iteratively refining the training data and retraining the model, they achieve better results compared to existing models, demonstrating the scalability of this approach for improving language models' ability to follow instructions. Section 2 Method. In our method, we use a foundational language model, a small set of initial data, and a large collection of unlabeled examples, like a web corpus. This unlabeled data is a vast and varied collection of human-written documents covering a wide range of topics. However, it doesn't come with any instructions. We make two main assumptions. First, we believe that within this massive collection of human-written text, there are sections that could serve as perfect responses to certain user instructions. Second, we assume that we can predict instructions for these potential perfect responses, which can then be used as high-quality examples to train a model that follows instructions. Our method, which we call Instruction BackTranslation, involves two main steps. 1. Self-Augmentation. We generate instructions for the unlabeled data, i.e., the web corpus, to create potential training data. This data consists of pairs of instructions and outputs for instruction tuning. 2. Self-curation. We select high-quality examples to use as training data. This data is used to fine-tune the base model to follow instructions. We repeat these steps iteratively. As the instruction-following model improves, it becomes better at selecting data for fine-tuning in the next iteration. We'll explain these steps in more detail below. To start, we use a set of human annotated examples as our seed data. These examples, which consist of an instruction and an output, are used to fine-tune language models. This allows the models to make initial predictions in both directions, predicting an output from an instruction and predicting an instruction from an output. We use a web corpus as our source of unlabeled data. We process each document to extract self-contained segments, which are sections of text that follow an HTML header. We then remove duplicates, filter by length, and eliminate potential low-quality segments using various methods, such as checking the proportion of capitalized letters in the header. Section Summary. The self-training approach described in this section assumes access to a base language model, a small amount of labeled data, and a collection of unlabeled examples. The process involves generating instructions for the unlabeled data to create candidate training data, and then selecting high-quality examples to fine-tune the base model to follow instructions. This iterative approach improves the selection of data for fine-tuning in each iteration. Section 2.2 Self-Augmentation, Generating Instructions. In this section, we'll discuss two key processes, self-augmentation and self-curation. In the self-augmentation process, we start by refining our base language model using pairs of outputs and instructions from our initial data. This gives us a reverse model, which we'll call m_yx, that can predict an instruction given an output. For each unlabeled example, we use this model to generate a potential instruction. This gives us a set of potential augmented data pairs. However, not all of these pairs are high quality, and using them all for self-training might not be beneficial. So, we need to curate a subset of high-quality pairs. This is where the self-curation process comes in. We select the best examples using the language model itself. We start with a seed instruction model, m_0, that's been refined using only the seed examples. We then use m_0 to assign a quality score to each augmented example. This is done by asking the trained model to rate the quality of a candidate pair on a scale of 1 to 5. We can then select a subset of the augmented examples with a score equal to or greater than a certain threshold, k, to form a curated set. We also propose an iterative training method to produce higher quality predictions. In each iteration, we use the curated data from the previous iteration, along with the seed data, to refine an improved model, m_t. This model can then be used to re-evaluate the augmented examples for quality, resulting in a new set of curated data. We perform 2 iterations of this process to get our final model, m_2. When we combine both the seed data and the augmented data for refining, we use tagging to distinguish between the two sources. Specifically, we add an extra sentence to the examples, which we'll call a system prompt. For seed data, we use the prompt answer in the style of an AI assistant, and for augmented data, we use answer with knowledge from web search. This approach is similar to methods used to tag synthetic data for BackTranslation in machine translation. Section Summary. In this section, the authors describe their self-augmentation and self-curation methods for improving the quality of the generated instructions. They first generate candidate instructions using a backward model, but not all of these candidates are of high quality. To select high-quality examples, they use a seed instruction model to score each candidate and create a curated set. They then propose an iterative training method where the curated data from the previous iteration is used to fine-tune an improved model, which is then used to rescore the augmented examples. This process is repeated for 2 iterations to obtain the final model. To distinguish between the seed data and augmented data during fine-tuning, they use tagging by appending an additional sentence to the examples. Section Seed Data. We've used 3,200 examples from the Open Assistant dataset as our initial training data, or seed data. Each example is a pair of instruction and output, taken from the first exchange in a conversation. We've made sure to only select high-quality responses, which are in English and have been ranked as top tier by human annotators. To fine-tune our models, we've used the pre-trained Llama model, which comes in 3 versions with 7 billion, 33 billion, and 65 billion parameters respectively. During the training process, we focused on optimizing the output tokens, not the input ones, which is a departure from the usual language modeling loss. We've used the same hyperparameters as most existing supervised fine-tuning methods. A learning rate of 1e5 that linearly decays to 9e6 by the end of training, a weight decay of 0.1, a batch size of 32 examples, and a dropout rate of 0.1. For fine-tuning with fewer than 3,000 examples, we've used a batch size of 8. We've named our trained llama-based Instruction BackTranslation model, Humpback 1, a nod to both camels and whales. For generating responses, we've used nucleus sampling with a temperature of 0.7 and a p-value of 0.9. We've also used the English portion of the ClueWeb corpus as a source of unlabeled data, from which we've sampled 502,000 segments. We've compared our approach to several baseline models. These include Text DaVinci 003, an instruction following model based on GPT-3 that's been fine-tuned with human-written instructions and outputs, as well as model responses and human preferences using reinforcement learning. We've also compared our approach to Llama, which uses llama models fine-tuned with 1,000 hand-picked instruction examples from a mix of community Q&A sites and expert-written instructions and responses. Another comparison is with Guanaco, which uses llama models fine-tuned with 9,000 examples from the Open Assistant dataset. Unlike our approach, Guanaco includes instruction output pairs from all conversation turns, not just the first. We've also compared our approach to other models that use data distilled from larger models like GPT-4, but we don't consider these directly comparable to our llama-based approach. Section Summary. The authors used 3,200 examples from the Open Assistant dataset as seed data to train their models. They used the pre-trained llama model as the base model for fine-tuning, optimizing the loss on output tokens during training. They also compared their approach to other baselines, including models fine-tuned with different datasets and approaches. Section: Evaluation. We've conducted an evaluation using test prompts from a variety of sources, including Vicuña, Self-Instruct, Open Assistant, Koala, HH_RLHF, Lima, and some that we've crowdsourced ourselves. In total, we have 1130 unique prompts that cover a wide range of tasks such as writing, coding, mathematical reasoning, information seeking, advice, roleplay, safety, and more. We've selected 250 prompts from this pool, excluding those in the Alpaca eval test set, to serve as a development set, and another 250 prompts to assess the quality of our generation. We've used both automatic evaluation with Alpaca eval, which calculates the win rate against baseline models based on GPT-4 judgments, and human preference evaluation. In terms of data statistics, we've provided the stats of the seed data and various versions of the augmented data in a table. It's clear that the augmented data tends to have longer output compared to the seed data. However, the self-curated higher quality training data, denoted as A4-2 and A5-2, has both shorter instructions and outputs among all augmented data, which is closer to the length of the original seed instruction data. We've also conducted a task diversity analysis of the seed data and augmented data. The distribution of the verb-noun structure of instructions in the seed data and augmented data, specifically in the A5-2 category, is visualized in a figure. The augmented data, like the seed data, has a few main tasks related to writing, information seeking, and advice. However, the content type from unlabeled data, such as articles, recipes, descriptions, releases, etc., complements those in the seed data, like essays, scripts, codes, stories, etc. Moreover, the augmented data enhances the task diversity, especially in the long tail. We've also explored the significance of data quality versus data quantity in learning to follow instructions. We've compared fine-tuning on augmented data of different quality. Specifically, we've compared fine-tuning on augmented data without quality-based selection, self-selected data in the A4-2 score greater or equal to 4, and A5-2 score greater or equal to 4.5 categories. The results, shown in a figure, reveal that training on augmented data without self-curation doesn't improve instruction following performance, even when the data quantity is scaled up. However, training on the high-quality portion of the augmented data leads to an increase in instruction following performance, with steady improvement as we continue to scale up the amount of augmented data. This contrasts with the superficial alignment hypothesis from previous work, which suggested that only a few thousands of high-quality instruction following examples are sufficient for aligning a pre-trained base model to follow instructions. Our results show that increasing the quantity of high-quality data provides further gains, while increased quantities of low-quality data do not. Section Summary. The evaluation of our model was conducted on a diverse set of 1130 unique prompts from various sources, covering different task categories. We used a dev set of 250 prompts and another 250 prompts for generation quality evaluation. The augmented data showed longer outputs compared to the seed data, but self-curated higher quality training data had shorter instructions and outputs. The augmented data also increased task diversity, especially in the long tail. We found that training on high-quality augmented data led to improved instruction following performance, while increasing the quantity of high-quality data provided further gains. Section: Data Scaling Efficiency. We're examining how different models perform when we change the amount of instruction following data they use. We're comparing these models to Text DaVinci 003, a model that's been fine-tuned with a 7B llama dataset. We're also estimating the efficiency of these models using a data scaling coefficient, alpha. This coefficient is determined by fitting the data to a formula where the win rate, W, is equal to alpha times the logarithm of n, the number of examples the model is fine-tuned on, plus a constant, c. We're comparing our method, which involves back-translation of instructions, self-augmentation, and self-curation, to other methods that use instruction datasets from different sources. Our results show that most instruction datasets that have been distilled are more efficient than those created from other sources, such as NLP tasks or community Q&A. We also found that increasing the diversity of instructions and improving the quality of responses leads to better data efficiency. When we scaled up the augmented data using the A5 dataset, we saw improved performance and more efficient data scaling. We also looked at how data and model scaling work together. We found that the trends we observed in the 7B models also apply to larger models. For example, the 65B seed model performed well, but adding high-quality augmented data from the A5 dataset improved its performance even more. We used Alpaca Eval, an automatic evaluation tool, to assess the quality of the model's output on 805 prompts from the Alpaca leaderboard. Alpaca Eval compares the win rate of each model to the reference model, Text DaVinci 003. We divided the models into three categories: non-distilled models, which are trained without any external model; distilled models, which are trained with a more powerful external model; and proprietary models, which are trained with proprietary data and techniques. Our method outperformed all other non-distilled models at both the 65B and 33B model scales. We also noted that Guanaco and OASST, which were trained on the same data source as our seed data but with more labeled examples, performed well. Section Summary. The section discusses the efficiency of data scaling in instruction following models. It compares the performance of different models using varying amounts of fine-tuned data and measures their win rate against a reference model. The results show that distilled instruction datasets have better data efficiency than datasets from other sources, and improving instruction diversity and response quality leads to better data efficiency. Additionally, the section verifies that the observed data scaling trends hold in larger models and evaluates the generation quality using Alpaca Eval, where the method described is the top-performing model among non-distilled models. Section: Human Evaluation. We carried out a human evaluation to assess the overall quality of the responses generated by our model. This evaluation was conducted on a combined test set that includes several existing benchmarks. For each prompt, we compared the outputs of our model with those of a baseline model. The human evaluator was asked to choose from three options. 1. The output from our model is significantly better. 2. The output from the baseline model is significantly better. Or 3. There's no significant difference between the two outputs. To avoid any bias, we randomized the order in which the models were presented. The results of this comparison, which included both open source and proprietary models, showed that the human preference distribution was consistent with the preference distribution when using GPT-4 as the judge. This supports our previous observations. We also evaluated our model on 5 common-sense reasoning benchmarks. These benchmarks, which include SIQA, PIQA, ARC-Easy, ARC-Challenge, and OpenBook QA, OBQA, measure reasoning abilities ranging from social interactions to science questions for grades 3 to 9. We calculated the zero-shot accuracy based on the perplexity of the correct answer, following the llama method. The results showed that our model performed better than the base model in social reasoning, challenging science problems that require more reasoning, ARC-C, and OpenBook QA. In terms of massive multitask language understanding, MMLU, our fine-tuned model showed improved zero-shot accuracy across all domains. However, it underperformed the base model when given 5-shot in context examples. We also conducted further ablation studies to understand the 2 key components of our method. To understand the behavior of our iterative self-curation procedure, we measured the performance of the intermediate models in selecting high-quality data on a development set of 250 examples with 20% positives, considered to be high-quality examples. The results showed that the self-curation performance improved in the second iteration in terms of selecting high-quality data. This improvement also corresponded to better instruction following when fine-tuning on the selected data, as shown by the win rate. An important observation was that even though the intermediate models did not have very high precision, training on the selected data still improved instruction following. This helps explain the effectiveness of our method. Section Summary. The authors conducted human evaluation to assess the quality of their model's responses compared to a baseline model, using a combined test set. The results showed that their model outperformed the baseline model, as confirmed by both human evaluators and the Alpaca Eval judge. They also evaluated their model on 5 common-sense reasoning benchmarks and found that it performed better than the base model in social reasoning, challenging science problems, and OpenBook QA. Additionally, they performed ablation studies to understand the impact of their method's key components, showing improved performance in data selection and instruction following. Section: Training on self-augmented data only. We're going to discuss the effects of training solely on self-augmented data. As depicted in the figure, if we train only on self-augmented data, without any seed data or self-curation, the quality of the instructions that follow doesn't get better. In fact, it might even get worse with more data. However, if we train on self-curated data, which is of higher quality, we see improvements as the size of the training set increases. Although this self-curated data doesn't perform better than just scaling up the seed training data, we notice significant improvements when we train jointly with both seed and self-augmented data. This suggests that seed data and augmented data complement each other. The seed data has the same distribution as the target domain, which in this case is the AI assistant's response, while the data from the web corpus can increase the diversity of the instructions and outputs. Next, let's talk about system prompts. In the table, we examine the impact of system prompts during joint fine-tuning and inference. We discovered that adding system prompts to differentiate augmented data from seed data is beneficial. Interestingly, using a combined system prompt at inference time, which merges the prompt for the seed data with the one for the augmented data, is more effective than not using a system prompt or just using the seed data prompt. This is the case even though this combined prompt wasn't used during training. Now, let's look at how adding self-augmentation data can improve the seed model. This approach improved the failure cases of the seed model for 16% of test prompts, which is 41 out of 251. We noticed better responses in several categories, such as reasoning, information seeking, and giving detailed advice, as shown in the table. The tables provide examples of how adding augmented data can enhance the quality of the responses. Lastly, let's discuss bias. Since the augmented data comes from the web corpus, one potential issue is that the fine-tuned model might amplify biases from web data. We tested the model's performance in recognizing potential bias using the Crows pairs dataset. We specifically evaluated the accuracy in identifying bias statements in 9 categories: gender, religion, race, color, sexual orientation, age, nationality, disability, physical appearance, and socioeconomic status. Compared to the base model, our fine-tuned models have improved accuracy in detecting biases, as summarized in the table. However, this doesn't mean that the fine-tuned model is less likely to generate responses that contain biases. Section summary. When training on self-augmented data alone, the quality of instruction following does not improve, or even deteriorates with more data. However, training on higher quality self-curated data brings improvements, especially when joint training with both seed and self-augmented data. Adding system prompts to distinguish augmented data from seed data is helpful, and using a combined system prompt at inference time is better than using the seed data prompt alone. Adding self-augmented data improved the failure cases of the seed model for 16% of test prompts, resulting in improved responses for reasoning, information seeking, and giving detailed advice. However, since the augmented data is sourced from the web, there is a potential for the fine-tuned model to amplify biases. The fine-tuned model has improved accuracy in detecting biases, but it does not guarantee that it will not generate biased responses. Section 4.2 Safety. We'll now discuss the safety aspect of our model. We've tested our model on 30 potentially sensitive prompts to understand its safety implications, as neither the seed data nor the augmented data were designed to include red teaming examples, and the fine-tuning stage wasn't optimized for detecting and reducing potential harm. Our findings suggest that the model tends to respond cautiously to these prompts, sometimes even refusing to provide information. We also found that using the system prompt from the seed data, denoted as S_A, often results in safer responses. This suggests that system prompts could be a useful tool for improving safety. We've included some representative examples in the table. We believe that incorporating red teaming or other safety measures into our augmentation procedure could be a worthwhile avenue to explore, especially since previous research has shown that instruction following models can self-correct morally to avoid producing harmful responses when instructed to do so. Now, let's talk about instruction tuning for large language models, LLMs. Our work aligns with the broader efforts to fine-tune LLMs to follow instructions. Early research in this area mainly focused on natural language processing, NLP, tasks, and found that fine-tuning with NLP datasets formatted as instruction output pairs improves cross-task generalization. More recent research has expanded instruction tuning to a wider range of general tasks, particularly those involving instructions from users of language models. A significant challenge in enabling LLMs to follow general instructions is the collection of demonstration examples for fine-tuning. Existing high-quality instruction following LLMs depend on human annotations at various stages, such as writing instructions, writing model responses, and indicating preferred responses. These instruction sets are often proprietary, with the Open Assistant datasets being a notable exception. However, the human annotation approach is hard to scale as it's expensive, time-consuming, and requires expertise in different domains. Several studies have explored using LLMs to generate instructions. For instance, GPT-3 has been prompted to generate more instructions using a few in-context seed instructions. The self-instruct approach uses the same method to generate instructions and their corresponding outputs, and also applies manually engineered filtering rules to remove low-quality instruction output pairs. Other approaches generate more complex instructions by creating variants of user instructions sent to ChatGPT. All these methods use model-generated responses for training data. Our method is similar to a concurrent work that uses human-written text as a natural response and employs the LLM to generate the corresponding instruction based on the response. However, we differ in two key aspects. Firstly, we emphasize the importance of the self-curation step in improving this procedure. Secondly, while they use an instruction-tuned LLM, Instruct GPT, to generate instructions, our approach doesn't rely on an instruction-tuned LLM and is instead an example of self-alignment. Section Summary. The safety evaluation of our fine-tuned model on potentially sensitive prompts revealed that it tends to produce cautious responses or even refuses to provide information, indicating a level of safety. Additionally, using system prompts from the seed data resulted in safer responses, suggesting that leveraging system prompts can enhance safety. While incorporating red teaming or other safety measures into our augmentation procedure could be explored further, our approach differs from existing work by not relying on an instruction-tuned LLM and emphasizing the importance of self-curation. Section: Self-alignment. Our research contributes to the expanding field of self-alignment, which involves using the model to enhance its own performance and align its responses with desired behaviors. This could include feedback generated by the model, critiques, explanations, and so on. However, our approach differs from others in that we enhance human-written web pages, while others generate training data in an unsupervised manner or use the model to create additional context to improve the output at the time of inference. We also focus on the quality of data. Several methods have demonstrated that the use of high-quality, human-written data can lead to excellent performance, as seen in projects like POMS and Lima. While some research provides algorithmic methods for filtering this data, our work is more focused on selecting self-alignment data. Our work also involves distillation. Many fine-tuned llama models are based on knowledge distilled from models like ChatGPT or GPT-4, as seen in projects such as Alpaca, Alpaca GPT-4, Vicuña, Falcon Instruct, OpenChat, and UltraChat. These methods require an already robust model and do not offer a guide for building a strong model from the ground up. We also discuss the limitations of these approaches in our work.